and the slides are always available the day after on our website, ie.ucsb.edu. And if you have any questions, please feel free to email me.
Okay, thank you. So it's my great pleasure and honor to introduce our speaker, Professor Bernard Kippelen from Georgia Tech. And a number of you students, especially in postdoc, that you got the opportunity to talk to Bernard today. And so here are a few people in the community that I would love always to come and chat with him or have certain data that I do not understand. I would come and pick his brain. Okay? Bernard actually born and raised in France, and he got all his degree in France, and he actually worked in the National Center for Scientific Research in France until 1994, and then he joined the faculty at University of Arizona, and so he was there for almost 10 years, and in 2003, he and his research group actually moved from Arizona to Georgia Tech, and as you can see, he received a number of awards in throughout his career. Some of the NSF Career Award, the 3M Young Faculty Award, and he also a fellow of the Optical Society of America and fellow of the International Society for Optical Engineering. And then you can see through his talk today, he had expertise in a number of research areas from optics to organic electronics, organic semiconductor, and device engineering. And so please join me to welcome Bernard.
Good afternoon, Quinn. Thank you for the nice introduction, and thank you, Guy, and the rest of your groups for the hospitality and for the opportunity to come to your beautiful campus. It's always a treat. Georgia is a beautiful place, but I miss the quality of the light here in the West. It's absolutely stunning. So I'd like to today share with you some highlights of work we've been doing over the years in the area of organic semiconductors. And like to, of course, acknowledge agencies that are shown here on that first slide who made that possible, but really highlight the fact that I'm just the privileged presenter today, but that many contributors participated and contributed to the work that we'll be sharing with you. There are too many to name all of them, but I also would like to mention that the field of organic optoelectronics is a truly interdisciplinary field of research. You can't master all these concepts from chemistry at the molecular level all the way to electrical engineering, and so none of the work I will be presenting today would have been possible without many discussions with collaborators, again, that are listed here from Georgia Tech and other institutions, people who are good friends and who I had the chance to interact with through the years. Okay. So organic semiconductors, why did I spend the last nearly 20 years working with these materials, and what attracts the students and young scientists that enter this field? And what I try to tell them is, because I truly believe that organic semiconductors have an opportunity to play a role in trying to solve some of the toughest problems that we're facing. And one of them is, of course, that constant increase in demand for energy, which is driven in part by the increase in population. If you look at the latest predictions from United Nations about the world's population growth, we've been probably around 9 billion people on the planet by 2050, which is in a very near future. And with all the challenges that that brings, because energy, of course, is related to many other things which are are important in maintaining or improving our quality of life, and we certainly don't want to increase energy production without worrying about the environment and some other important aspects that are linked. So we have to look at this on a global scale, and food and water, of course, is very important. Some other aspects such as healthcare and security. And so the bottom line, because of that huge challenge, there is a need for innovation. Okay, and innovation is not something you can avoid. It's really necessary for multiple reasons. And there are many kinds of innovation. One way to classify innovation is this is a language and terms I borrowed from Clay Christensen from his book The Innovator's Dilemma, and he kind of divides innovation in two main types of innovation. One that he refers to as sustaining, okay, which is certainly, for instance, was the case in storage technology, where you keep making next generation of devices or systems that have improved performance, and these are well-defined markets. Okay, you know who your customers are, and they just want better devices. And we, as cell phone users, for instance, certainly are on that curve here, where every maybe 18, 24 months, we kind of get a device with more computational power and better displays and so on and so forth. And a lot of these move the market needs, otherwise you can't really get into the market. But there's a second kind of innovation, where in the early stages nobody really pays much attention to that type of innovation because there is no real solid market for it, or the market size is very small. So if you want to grow your business, you should be ignoring little markets and really focus on existing markets or large markets. Okay. However, and there are many examples of this, sometimes the technology will catch up with sustaining path very rapidly, and so you can see the slope here in terms of improving performance can be much steeper than when you are on that sustaining curve, even though you are well below. And the critical point is to reach maybe a different market that has a lower end needs in terms of performance. And I believe that organic semiconductors are a disruptive technology, and a lot of the evolutionary trends right now are showing this, especially the pace at which, for instance, the power conversion efficiency of plastic solar cells has been growing in recent years, is consistent with that picture introduced by Clay Christensen. Okay? So the foundation of these devices that we build, which are relevant to energy, not just for energy production, but also energy efficiency or energy savings, are organic semiconductors. I don't want to go too much into the details of the chemistry of these materials. I'm a physicist by training, an electrical engineer after all, and many chemists here probably in the audience who know these things better than me. But what I find fascinating about organic semiconductors is the fact that the properties that you get in films at the macroscopic scale actually have a lot in common with some of the molecular properties. And that you can make films using very simple either vacuum-based techniques or wet processing techniques using standard printing or coating, and you get films which contain large densities of impurities and defects, and you have a lot of disorder, but yet you still have mobility values which are comparable to amorphous silicon or even better, and for a lot of the devices that I will be talking about are good enough. And so the fact that these materials have electronic properties which are very tolerant to defects and imperfections also allows you to fabricate these films at low temperature. So room temperature is okay, and that of course is important in terms of manufacturing, because we're talking about energy and energy savings. We also like to develop technologies where the manufacturing itself is done at much lower energy, where you don't have to heat up materials to 1,000 degrees Celsius and so on in order to grow semiconductor layers. And so what you gain also in addition to, because you do that low temperature processing, is that your films can be deposited onto substrates, including on substrates that usually wouldn't withstand these high temperatures that are used to grow other materials. And so you can envision, this is kind of the vision of having flexible printed electronic devices with various functionalities at relatively low cost of a large area, and using equipment for the manufacturing of these devices, which requires much lower capital investment. And so that's kind of the dream and the goal here for these materials. And so my presentation, as I said, consists of highlights, and I thought I will give you some, share with you results of studies we've made in 3 categories of device platforms. These all somehow relate to energy. The first one, organic light-emitting diodes. As you will see, they're already now widely adopted for displays. They will also play a role in solid-state lighting. High efficiency means that we'll be able to have energy savings, electricity savings. Organic field effect transistors, I think, have a role to play in making smarter devices, smarter homes, smarter grids, again, that can lead to energy efficiency. And then, of course, the third part, organic photovoltaics, which is really the generation of power. Okay. So let's start with the first one, which is organic light-emitting diodes. And you know, the dawn for that technology has really arrived. It's been long awaited, but after many years, finally now that technology has been widely adopted in thin displays, and in part because of investments by companies like Samsung, for instance. And so if you own a Samsung Galaxy phone, most likely you have an active matrix OLED display in your pocket. And as you can see, it's, you know, these are forecasts, so sometimes they're a little bit over-optimistic, but certainly it's something that will continue to develop and gradually gain market share over liquid crystal displays, because it has many advantages. And so one of the starting point, or the genesis of that field, was the work of Ching Tang and Steve Van Slyke at Kodak in the early 80s, who demonstrated light-emitting diodes with a quantum efficiency of about 1%. And so that kind of started to get people's attention. And the general structure of devices like this is shown here on the right-hand side. This typically has the structure of a diode. You start with a piece of glass which is transparent, which is coated with indium tin oxide high work function electrode. You deposit a few layers, one for the injection of holes, one where the holes and electrons create excited states, and the relaxation of these excited states back to the ground state leads to light emission, and the light is usually emitted through that transparent substrate. And for the injection of electrons here on top, you have that low work function electron. Now, the problem in terms of efficiency of these early devices is that it was based on the fluorescence of these light emitters. And so if you look at the electronic states of these organic molecules, and you're creating excited states through the injection of holes and electrons, you can form either singlet states or triplet states, okay? And in these fluorescent molecules, only emission can take place from the singlet excited state back to the singlet ground state, because the transition here from the triplet state is forbidden, okay? Which kind of limits the overall internal efficiency of these devices to the singlet-triplet branching ratio, which was 25%. But in the late 90s, Mark Thompson and Steve Forrest introduced these electrophosphorescent materials. So you take a a molecule, fluorescent molecules, but if it contains a heavy element, such as iridium or platinum, because of spin-orbit coupling, you can actually get emission from what is no longer really a triplet state here, but kind of mixing of singlet and triplet state, but you lift the constraints here, and you can get emission from that emissive state, and you can harvest all the singlets and the triplets that are formed in that emissive layer, and you can transfer the singlet excited states to the guest molecule or the dopant by dipole-dipole long-range Foerster transfer, or you can also harvest the excited states which otherwise here in the matrix would be non-emissive to the guest through exchange short-range Dexter type energy transfer. Okay, and so by doing so, you can get internal efficiency of 100% because you can harvest all the singlets and all the triplets. Of course, the light that is emitted is also limited by how much light gets trapped into the structure by total internal reflection. So in a lot of these early devices, the emission takes place through that transparent electrode. And another problem with a lot of these structures that usually for the cathode, in order to efficiently inject electrons into these organic semiconductors, you're using metals which have a low work function. And these metals are highly reactive. And so if that's on the top, you have to protect it very well with an encapsulation layer. And so some of the things we focused on recently is to change the structure or the geometry of the device. And so rather than having emission from the bottom, which limits, for instance, the pixel aperture ratio, if you combine these light emitters with a backplane technology, such as in an active matrix OLED display. And so you really have advantage of having the emission take place from the top. And what we also did is we switched the polarity of the diode, namely we have now the buried cathode here, which is more reactive at the bottom of the device, and the anode, which is made of out of metals that have high work function and are environmentally more stable. The other advantage also of having the cathode at the bottom is that it's easier to integrate your diode with some of the drive electronics that are being used to control the display, because most of the transistors here that are being used right now for the backplane technology are N-type or NMOS type circuits. So you'd like to have the diode with that polarity here on the drain side of the transistor. So let me share with you some examples of these devices that my students Ehsan and Keith fabricated. And here you can see that's the structure of that emitter. So you see that it contains iridium. And we'll see that's kind of a problem because these rare metals are pretty expensive. And so using can give you a high efficiency. There is a cost associated with that. And now cost is a barrier for the massive adoption of some of these materials for flat panel display technologies. But you can see it's a fairly complex stack here where the electron injection is done by that lithium fluoride aluminum cathode, which is now at the bottom. Here we have an electron transport layer. We have that emissive layer. We have a whole transport layer, moly oxide, and a very thin layer of gold is used as the anode. It's on top, and because the gold is sufficiently thin, it's semi-transparent, and the light can go out through the top of the structure. If you look at the performance of a device like this, you can see that you can get external quantum efficiencies close to 30%. Again, there is also another advantage using ITO, is that you can really build these device architectures on flexible substrates because these thin metal films are very robust to bending, while ITO is fine on glass, but as you start to make it on plastic at the low bending radius, it starts to crack. Okay. The other thing to note also is the very high luminance of these devices, so you can get several 100,000 candelas per square meter at relatively low voltages. Of course, there's a little bit of roll-off here, but overall high performance. These are single junction devices. Now, one way of further increasing the performance of these devices is to start to make multi-junction devices, or in other words, to stack these diodes. But again, here we stack them in a way such that they are in the so-called inverted structure, where the cathode is at the bottom, and you have cathode that charge generation in the middle, and the top electrode is an anode. And so here's the structure and performance of a set of devices. You see the curve in black here is the external quantum efficiency, and here the light output of a single layer diode. If you take a double layer diode, you can really nearly double the efficiency, because for the same current, the current is now flowing through two junctions, and so you have two junctions that emit, and so you have a higher light output. If you play with that light outcoupling layer here, and you add a thin high index layer on top of that top electrode, you can further increase the performance of your device, and you can significantly increase the amount of light that is coupled out of this device. And so you can see that now with these multi-junction devices at 1,000 candelas per square meter, we can get 200 candelas per amp. And at 100,000 candelas per square meter, which is a really bright device, you can still get about 100 candelas per amp. So a lot of light, and you have to start worrying about protecting your eyes when you deal with light sources like this. So far, these results were obtained using these organometallic compounds. So the emitter was an iridium-containing compound that emits in the green, and for a long time, the community, we thought, okay, this is it. That's going to be the material of choice, and this the best way of harvesting singlet and triplets. However, in recent years, and these concepts were proposed quite some time ago, but I think Shihaya Adachi in Japan deserves a lot of credit, because he really he believed in that approach, and he pushed this to a level where now, as you will see, we can get performance levels that are comparable to the organometallic compounds, but with all carbon or kind of all organic low-cost constituents. And the concept here he refers to as a thermally activated delayed fluorescence. And the idea is that, remember from what I said earlier, in typical fluorescent materials, you just have the fluorescence, which is the emission from the singlet excited state. Okay? And usually you don't have emission here from the triplet. But if you bring the triplet energy here, or the triplet level close to the singlet level, you can somehow create singlet states from the triplet states through thermal activation. So you're kind of regenerating singlet states that are emissive from these triplet states. And you can do that without having to use rare metals or rare earth elements, such as that iridium compound. And so on the right-hand side is the chemical structure of one of these TADF emitters. So you see it consists of the core here is a benzene, and then you have these 4 carbazole functionalities. Usually the HOMO, the highest occupied molecular orbitals, are located on one of these carbazole groups, and these cyano groups here, strong acceptors, that's where the LUMO orbitals are located. And compounds like this exhibit very strong thermally activated delayed fluorescence. And so we took one of these compounds here, and we mixed it into one of these host materials that we developed earlier. And the rationale here in the design of these molecules was, again, to get ambipolar materials that transport holes and electrons quite well. So again, we have carbazole groups here, and that sulfone group here, which has electron transport properties. And by mixing that TADF emitter into a host like this, and in a traditional device here with ITO and gas, we can get the following performance. So you can see on the left-hand side, you have the current density versus voltage. These devices turn on at fairly low voltage. Quantum efficiencies, which is shown here, the order of, or in excess of 20%, which is comparable to the type of efficiencies that before one thought that one could only get with these compounds, organometallic compounds that contain these heavy rare metals. Okay, so you know, this is kind of an indication, and this is in the green, but we have now results also in the blue that indicate that you can get performance levels in these much lower cost materials because of that approach using that thermally activated delayed fluorescence, and you know, get efficacies both in current and power that are quite attractive. Okay, next I'd like to change device platform and talk about field effect transistors. Okay, the transistor is really the building block, allows you to build all kinds of circuit with a lot of different functionalities. And there's also a field where there has been a lot of progress. The mobilities of these transistors keep going up, I think, the performance. But for a long time, one big issue has always been, or the biggest concern has been, the stability of these organic semiconductors, because organic molecules can be quite reactive, especially in presence of oxygen and moisture. And you know, if you want to deploy these things, they have to be robust and really stable. And so some of the work I decided to talk about in this area today is not about making the transistor that has the highest mobility, but show you that you can build device architectures that are very robust. And what's behind that a device architecture with good stability is a process which is called atomic layer deposition, or ALD, which is something that was developed for conventional CMOS technology, where you can make very high quality, dense and pinhole-free dielectric layers from the repetitive reaction of different precursors. In this particular case, it's just a cartoon showing how you can grow aluminum oxide films, where you have water and trimetal aluminum, and that by alternating these precursors and in between purging the chamber, you can grow layer by layer very high quality dielectric layers, and with fairly high dielectric constant also, which is quite interesting because you want the high dielectric constant to increase the capacitance density of your gate insulator to decrease the operating voltage of your transistor. And so the use of ALD in organic field effect transistors is something we pioneered back in 2006, 2007, and we've demonstrated complementary circuits with materials like pentacene and C60. But here, oops. Thank you, Microsoft. Okay. It's fine. Gives me time to recover a little bit. Okay, so what is particular to the architecture that I'm sharing with you here is the use of a gate dielectric which is comprised of a bilayer. Okay, so you can see this is the cross-section of a transistor. You have a substrate. We have a source and drain electrode, so just patterned gold electrode. We have a layer of a semiconductor here, which is TIPS pentacene. These molecules developed by John Anthony at the University of Kentucky. That's mixed in that polymer matrix that's spin-coated. And then we spin-coat first a thin layer of a perfluorinated polymer, such as Cytop. The choice for the perfluorinated material is that usually these materials, they are processed from solvents that are orthogonal to the conventional solvents that are used to process the semiconductor. So when you spin coat that layer on top of the semiconductor, you get a very clean and sharp interface here with very few defects, which is important for the stability of the transistor. But cytope itself has a fairly low dielectric constant, so that's the problem. But if you grow another thin layer of aluminum oxide on top of that thin layer of cytope, you get something that has a relatively high capacitance density of the order of 30 to 35 nanofarad per square centimeter. And so you can get transistors that have a fairly low operational voltage. But what really surprised us was the stability of these transistors. Okay, here's first stability on the cycling. So you can see 20,000 cycles, and there is no shift in threshold voltage. There is no degradation whatsoever in the performance of these devices. They're also very stable under continuous operation. And so, you know, these devices were sitting just like this in the lab, and Do-Kyung, my postdoc, every week would put it back in the semiconductor parameter analyzer and measure the transfer characteristic, and he didn't see any change. So at some point, he started to be really impatient. He said, okay, I'm going to beat these devices really hard, okay? And so the first treatment was pretty dramatic. He actually decided to take these devices and after characterization, these are devices that had been fabricated 11 months ago. He decided to put them, like shown here, with no additional packaging or anything, into a plasma chamber for 5 minutes. Say, okay, this is going to do these samples, right? But to his surprise, when he took the samples out and he put them back and then measured the transfer characteristic, you could still get a transistor performance. Next, he said, okay, let's see the influence of water. So he took these samples and he immersed them in water for an hour, okay? Just dried them and put them back in, and to his surprise, the transistor was still working. Now, I should mention that, of course, he's also made reference or test structures where he had only cytope as the gate dielectric or only aluminum oxide grown by ALD. These devices don't, after you put them in a plasma chamber, they're done. Nothing works anymore, okay? So just to show you in more details what these different processing conditions do to the transistor, that's a transfer characteristic of a transistor right after fabrication. The device has never been exposed to air. And I apologize here, when he did this, these are pretty ugly transfer curves with a lot of contact resistance. We have now transistors with very clean transfer curves, but square low. But here it was just for the purpose of stability. So if you take these devices and you leave them in air for some time, you see changes in the transfer characteristic, but it stabilizes. But here is before and after the 5 minutes in the plasma chamber. So, okay, not only do these transistors still work, but you can see there is very little change in the transfer characteristic. This is before and after 1 hour immersion in water. Okay, again, almost very little change. And so just to illustrate that, you know, organic semiconductors can be made very stable if you incorporate them in the right device architecture. And then, of course, here, that particular bilayer gate dielectric is also a good barrier. It protects the semiconductor from the environment, so it works quite well. This is just to illustrate that you know, we can make transistors with that bilayer gate dielectric that have now very clean, very nice transfer characteristics. On top here, this is an N-channel transistor with that commercial active ink from Polyera. And at the bottom here, you see another example. It's not as clean as this one. There's still a little bit of contact resistance, but this was done with a soluble molecular compound that was synthesized in the Marder group, and both lead to mobility values of the order of 0.1 to 0.2 square centimeter per volt second. Okay. Now remember, these devices are so stable in water, we started to use them as sensors. And so one of my postdocs started making microchannel devices out of PDMS and started to run a continuous water flow on top of these transistors. Okay, there is no degradation under continuous water flow, and we wanted to test these devices as sensors, and so we introduced a cysteine here in the water, and then we just run regular water, included cysteine, run regular water, and so on and so forth. You can see over time periods here, which are hours, and you can see that is a perfect reversible, non-destructive sensing of analytes using these transistors. So you can do sensing, but it's really non-destructive sensing, which is really important. Okay. Last part of my talk, I'd like to discuss with you some work we've done in the area of organic photovoltaics. And so I don't want to spend too much time about the latest understanding or how organic solar cells work, but based on the recent studies that we've done, we feel that they just operate, or you can describe them like any other solar cell, namely that you have somehow a device that's asymmetric, that absorbs light, and where you have a mechanism by which electrons and holes accumulate in a different part of the device and are extracted by different electrodes. So here I use some color coding. I'm going to use the red color to describe an electron collecting electrode, a blue color for a hole collecting electrode. Okay. And so the analogy, let's say if you're familiar with a conventional PN junction type or crystalline silicon cell, you have your asymmetric device where, on one side you have a p-doped layer, on the other side you have the n-doped layer, and in the middle you have that membrane that separates holes in one direction and electrons in the other direction. Here, that asymmetry in organic solar cells is caused by the fact that you're mixing donor and acceptor-like compounds which have different electron affinities and different ionization energies, and you make transfer of charges asymmetric. You tend to have electrons being transferred and ending up on the acceptor. You end up having holes transferred or ending up onto the donor, and you also use metals with different work function to effectively extract electrons on one side and holes on the other side. And so that's shown here, where, remember, a solar cell is producing power under illumination. Power is measured in watt, so watt is voltage times amps. So you need simultaneously a photocurrent and a photovoltage. If you take that absorber here, which has two levels here, one for the transport of holes and another one for the transport of electrons. What I mean by absorber here, complex mixture of a donor and acceptor, which is still a very active field of research, trying to figure out what the real morphology is of these mixtures. But this is the energy level diagram in the dark at equilibrium, where you line up the work function of the metals with the Fermi level for your absorber. And on the right-hand side here is a schematics of what happens when the solar cell is operating, where you're now creating holes in the device, you're creating electrons, you have spatially separated the holes and the electrons, and their density is described by these quasi-Fermi energies, which is the electrochemical potential for holes and electrons, and you get a photovoltage, which is the difference between these quasi-Fermi levels at the two electrodes, and you get a current, which is described by the gradient of the quasi-Fermi levels, or the gradient of the electrochemical potential. Okay? And so you see these diagrams, and because of the need of an asymmetry in a solar cell, is that you need both high and low work function electrodes. And the challenge with a low work function electrode, as I mentioned earlier in the context of OLEDs, is that usually materials such as calcium or lithium fluoride and so on are highly reactive, and so that limits the stability of these materials unless you use a very expensive encapsulation technology, which we can't afford, because the game in solar is really you want to lower the cost as much as possible. And so by serendipity, one of my students, J1, actually came across a very interesting observation. He was using that compound shown here, which was a surfactant, because he was making solar cells where he was trying to fabricate a TiO2 layer for electron collection. And he observed that the more surfactant he was using, the better the solar cell. At some point, I asked him if he had tried to just use the surfactant by itself, and he had not, but he went back to the lab and just dipped ITO into a dilute solution of that compound, measured the work function of just clean ITO and ITO coated with that PVP, and he saw a significant reduction in work function. We didn't quite really understand what was going on, but that's where having collaborators is very helpful, and so we sent some of these materials and samples to Antoine Kahn at Princeton, who did some UP. The onset of these secondary photoelectrons in UPS is shifting to the left here, which is an indication of a shift down of the vacuum level, which is what you usually observe when you have formation of a surface dipole at that interface. And so back to the structure, we're trying to figure out what could cause that dipole at that interface, and the suspect here was that nitrogen. And so we started picking the Aldrich catalog and looking for a lot of molecules or polymers that contain these amines, and one of them was PIE, another one PEI. And when we now changed or modified the surface of ITO with one of these polymers that contained a large number of amines, you can see now the shift is even larger. And it doesn't just work on ITO, it also works on gold. It works even on conducting polymers. Okay? Some DFT calculations on some model compounds here by Jean-Luc Breda, also kind of consistent with the picture that we have a partial charge transfer of these donor-like compounds onto the metal surface, and that these surface dipoles are responsible for the shifts in work function. And of course, the advantage of that technique compared to low work function electrodes is that it's fairly stable up to about 200 degrees C, and also fairly stable in air. The first step was to validate that we could use that modification of work function, and so decreasing the work function of ITO down to about 3.6. Excuse me. And so, sure enough, you can get fairly good solar cells, okay? Fairly good efficiency here, okay? Now, remember I showed you that you can use that modification to also lower the work function of conducting polymers. And so we could make low work function conducting polymers, and that enabled us to fabricate a solar cell where all the layers were actually made from organic, completely plastic layers. And so the structure shown here, where we have a polyethylene sulfonate substrate. We use a P.PSS formulation that has high conductivity, pH 1000. Modify it with one of these nitrogen-containing or amine-containing material that constitutes a low work functional electrode, so it's electron collecting the active layer, and then we put P.PSS, regular P.PSS, as the high work functional electrode. And you can get fairly reasonably good devices. But something that has been bothering us for many years, and as we started to fabricate solar cells with Pentacene and C60 in the early days, we could fairly well model these solar cells with that well-known equivalent circuit model here. And we felt good about this, but as soon as we kind of looked at the current voltage characteristics of bulk heterojunction solar cells, you can see from the dark current here in a semi-logarithmic representation that the shape here was slightly different from what you expect from an ideal diode. So here, these are the conventional linear plots. So you see the current voltage characteristic in the dark. You see the current voltage characteristic under illumination. And the inset is just a semi-logarithmic plot here. So you see in that first device that if you measure the current level in reverse bias in the dark, you get currents here at -1 volt, which is of the order of 100 microamp per square centimeter. Okay? If you take a device like this and you measure the open circuit voltage as a function of the short circuit current, which here is just scales with the illumination or the irradiance of the solar cell. So you start here at 1 sun, okay, where you get about 10 milliamps, sorry, that's microamps, so yeah, 10 to the 4 microamps per square centimeter is about 10 milliamps per square centimeter. And you start to reduce the light, okay, by about 2 orders of magnitude. You see a reduction in VOC, as you expect from that simple, you're just inverting the Shockley model of a diode. But very rapidly, things kind of changed drastically. And we were really puzzled by this for a very long time. However, occasionally, and these were really kind of outliers, which initially we disregarded, you would have devices where now, in the dark, in reverse bias, the current was below 10 nanoamps per square centimeter. Okay? And if you actually take a device like this, and now you do the same, you vary the intensity, and you measure the open circuit voltage, you get the red curve here. Okay? So now you can see that the voltage actually followed that simple Shockley diode relationship. This is just a Shockley diode inverted to express the VOC as a function of the current. Now it fits perfectly well. Okay? You see that it's actually consistent with what a Shockley model predicts, and this is just kind of a summary of these different steps. And so the conclusion here is that if you measure a high current in the dark in reverse bias, which is, means that you have a low shunt resistance, because these devices most of the time are dominated by these parasitic effects, then you get that kind of behavior which is not typical for a diode. But if you have devices where the shunt resistance is large enough, and there you can actually vary the light level by 6 orders of magnitude, and it follows perfectly well the behavior of a diode. And this can be seen here. These are just calculations based on the equivalent circuit that I showed earlier. The only thing we do is we vary the shunt resistance from about 100 ohms square centimeter all the way up to about 100 mega ohm, or even this is 1,000 mega ohm, giga ohm per square centimeter. And you can see that the shape now of these curves are very typical of what we see in these low and high shunt devices, where when you look at in forward bias also, if you have a low shunt resistance, you see that part is just an ohmic behavior due to the current flowing through the shunt resistance before the diode turns on. If you increase the shunt resistance, you see that the diode kicks in much earlier because you have much less leakage. Now, you might say, okay, you see that in very few devices, and it's not a majority of the devices. But actually, if you change the way you fabricate your devices, and here is an example of another all-organic or completely plastic solar cell, in which instead of using spin coating, we transfer laminate some of these layers. Okay, so the active layer is transferred from another substrate, and the top electrode is transferred also. And in layers like this, you consistently see a very high shunt resistance, and sometimes you can't even resolve the shunt resistance because it's below the detection limit. Okay, and so this is again VOC versus the current or the light in these all transfer laminated devices. You see you have a very, you can fit very well that Shockley diode equation over 6 orders of magnitude. And then from that slope also you can calculate the ideality factor of your diode, which gives you information about the type of recombination. And you can see that the reverse saturation current, which you can derive from the intercept of that curve here, is actually typically in the picoamp or tens of picoamps per centimeter, much lower than what one would measure in where most of the time the current that you see is limited by shunt resistance. Okay. Before I wrap up, I just want to share with you very rapidly this is just one study in an effort to try to see if we can make organic solar cells even greener. And the idea here was to show that can we make solar cells that can be recycled more easily than plastics. Plastics are a source of concern. If they end up in the landfill, you're going to create an environmental problem by trying to solve one, and we don't want that. And so a first step was to try to see if one could actually replace some of these materials with materials that are derived from natural feedstock rather than from oil as a feedstock. And the answer was cellulose. And so you're all familiar with the process by which you transform wood into paper pulp and make paper is fibrils, but paper is fairly rough and it's difficult to fabricate solar cells and the printed electronic devices on top of paper because of that roughness. But if you go a few steps further and you break down paper pulp, you can break it down into these cellulose nanocrystals, which are a few hundred nanometers in length and a few nanometers in diameter. And these can form films and solids through hydrogen interactions. And if you blend some of these cellulose nanocrystals with some glycerol, you can fabricate transparent films. You barely see the film here on the tweezers. It's fairly optically transparent, but more importantly, it's very flat. The surface roughness is down to a few nanometers, and so we could build solar cells on devices like this. Efficiencies now are about 4% in these devices, but what was interesting to see is the ease of recycling of these materials. If you take these solar cells within a few minutes at room temperature, the substrate redissolves, and you thin active layer in that solution. So if you filter the solution, you can remove and then what's left in that filter, if you use an organic solvent, you can recover also the active layer, which is shown in the next step here. You add now organic solvent, and you see from the coloring here, you're redissolving the active layer that was on the filter, and you'll end up with just the metal used in that particular device geometry. Okay, so I think my time is coming up, and so just to wrap up, I hope I convinced you that there's still a lot of room for innovation with organic semiconductors, that a lot of these activities, I think, will impact energy in terms of energy production, but also energy efficiency, developing smarter technology, and also developing light technologies that can lead to power savings. And so with this, I'd like to thank you for your attention. Yes, so that's part of it. It's part of it. But on the other hand, you know, the way you measure the performance of a barrier coating is so-called calcium tests, where you deposit calcium sensors, and then you deposit the barrier coating on top of the calcium, and you measure how fast the calcium disappears, because calcium reacts in contact of oxygen and moisture. And actually, when you measure the metric there is water vapor transmission rates. And the water vapor transmission rates of these bilayers is not that great, okay? So I think it's also a conjunction of the fact that these TIPS pentacene molecules are fairly stable because of the substitution in these reactive positions. My colleagues, chemists, can probably speak more to this. But yeah, it's a combination of the stability of the semiconductor itself, and then there's clearly a synergy between the type of perfluorinated material that we're using and the ALD process itself. Because if you just deposit a thin dielectric layer by using PECVD, for instance, on top of the CyTop, you don't get the same result. So it's also the fact that ALD, because you go through these precursors, it's almost like it's sealing the pores and the defects in the polymer layer, and we're still kind of trying to figure out completely what's special about that combination. But it's not specific to CyTop. You can take other perfluorinated materials. And when you think about it, initially it doesn't really make sense because the steps of growing ALD films is through hydroxyls, right? OH groups. And on a perfluorinated material, you don't expect to have a high density of such. So there's a lot of unanswered questions here and still question marks and mysteries. But certainly the stability is mind-boggling.
The ALD technique to be universal for other systems like maybe polymers? Or is it just in TIPS pentacene that you guys have seen?
Oh, no. So that architecture works with any transistor. So including metal oxide, indium gallium zinc oxide. Actually, the examples I showed where we had better transfer characteristics, these were for transistors with different semiconductors. And again, you have the same benefits in terms of stability. So you can see here, these are actually, the TIPS pentacene is a p-channel transistor. These are n-channel transistors. And you get nice transistors with low operating voltage, and the stability of these devices is we have a review paper where we discuss the stability of N and P channel transistors. There are small differences with respect to the stability and the doping effects and so on. But overall, it's fairly universal. It works quite well.
Other questions?
So, just a quick question for the cysteine detector.
Yes.
What's the transduction mechanism? Is it interacting with the...
Yeah, so what I forgot to mention, I apologize, I didn't have much time to provide you with the details. The top gate metal electrode is porous. So there is some porosity. And so the analyte basically penetrates in through the porous top electrode. And what's changing the properties of the transistor, we believe, is the interface between the gate metal and the gate dielectric. And so this is why it's very stable and non-destructive, because we don't touch the semiconductor dielectric interface. What's causing the transduction is done at the metal dielectric interface. It doesn't percolate, it doesn't go through the dielectric. So the semiconductor channel is untouched.
So you're changing the capacitance of the...
Yes. Yeah. And so you can also actually, the same transistor geometries work as pH detectors. We can, if you change the pH of your solution, you see a change in current. I think I have it in the supplementary slides, if I'm not mistaken. No, I didn't put it in here, but yeah, we have paper on it if you're interested. Same reference as
Other questions?
the cysteine sensor.
I had had a question about the thermally activated delayed fluorescence. So I guess you're kind of trading spin orbit coupling to do the spin flip with electron photon coupling to transfer kind of on those two. The schematic kind of looked like two potential energy surfaces.
Yeah, it's basically a thermal process by which you recycle singlets from triplets.
So what is the rate of that transition? Is it
It depends on the singlet triplet energy difference.
yeah.
And the trade-offs is that if you make those, if you really your HOMO and LUMO become too orthogonal, then you also start to have less oscillator strength. So you're affecting the whole transition itself. Okay, so there's kind of a sweet spot where I think you have to find the best conditions where you can minimize that energy barrier, but also you don't want to compromise the oscillator strength.
Just related to this question, in your experience, Bernard, have you seen any difference in the roll-off effect between the phosphorescent emitters and the...
No. We just have a paper that appeared where we compared the performance of these TADF devices with reference devices based on CBP. And the roll-off is kind of similar. We believe that the roll-off has a lot to do with balancing hole and electron currents over the full voltage range, right? Because you want to balance both currents. You can balance it at a given voltage, but if the rate of hole and electron injection are very different as a function of voltage, then you see roll-offs. But again, you know, OLEDs is interesting because they have reached a level of performance which is remarkable. But every time we think, okay, we understand now what's happening, and we design a Gedanken experiment, and we make the device, and we say this is what we should see, quite often you see something different, which means that our level of understanding and our level of control is still probably, not good enough. So we have to continue to investigate and work on this device. But I think, you know, the TADF is a very good example where people thought, well, you know, OLEDs are now widely used in industry, in the marketplace. Why should we continue to work on these issues? And, you know, all of a sudden, something like this new wave, a whole new field emerges. And I think that's the beauty about science. And I think there are a lot of excitement and surprises to come. We just have to continue to push this field. And I think that organic semiconductors are still in their infancy, and that there is much more to be learned. It's a great area to work with, and that's a message, you know, to the students who are planning careers in that field. I mean, this is the right time. This is exciting, and I'm sure there will be more excitement in the years to come.
Any other questions? Okay, so if not, please join me to thank Bernard for a wonderful lecture.
Thank you.